and welcome to the third day of Qubes OS and 3M Dev Mini Summit 2020. And I'm Piotr Król, and I will moderate this call today. And let's start. Maybe a couple words. I hope we will have very interesting discussion today, since we have more participants on Zoom call. I believe Daniel Smith, trench boot maintainer, will join us today. Andrew Cooper from Zen is with us. Marek Marczykowski-Górecki from Qubes OS. And we have also some additional members from 3M Dev, especially Christian Hebel, who's responsible for development of landing zone, a trench boot component. So I believe today there will be very interesting discussion about D-RTM. Of course, some people have to drop because of other calls. So definitely the first part will be more. We'll have more participants, and then we will continue second part with more practical approach. But let's present the plan. Of course, this is day 3 organization. It's the same as always. So 30 minutes first presentation, 15 minutes discussion between Qubes OS team and 3M Dev team and other participants on the call. Then we have questions from chat. Then second presentation, another discussion between participants on chat on Zoom call. Then we're taking questions from chat, from YouTube chat. And then we have Ask Me Anything, mostly focused about D-RTM in Qubes OS for DOM0, but also for VMs. And I hope we can extend that discussion to Zen and in general to hypervisors. Okay, so let's start with my presentation. D-RTM. So D-RTM for Qubes OS VMs, or this maybe would be very general because it can be applied to also other projects. So what we will talk about, first some intro for the people that didn't watch previous days, goals of this presentation, a little bit about terminology. I will talk a little bit about Flickr, which is kind of first try of using the features in very interesting way. I will explain that further. A little bit about how we can do platform relaunch with D-RTM and how those two functionalities play together. Virtual machine introspection and D-RTM, VTPM and D-RTM. Then I will show some architecture of network booted VDL, dynamic launch measured environment, virtual dynamic launch measured environment. Then I will show some possibility of using that in Qubes OS by visual trust level indicator for VMs, and then some future ideas and discussion. Okay, my name is Piotr Król. I'm founder and embedded system consultant at 3M Dev. I'm very interested in open source firmware and platform security, and recently also this is associated with trusted computing. So what's the goal of this presentation? Mainly we want to discuss value and usage models of D-RTM, dynamic root of trust for measurement implementation in Qubes OS and also in other operating system that use Zen or other hypervisors. I definitely would like to thank Daniel and Andrew for reviewing the presentation, also Marek for being here and helping reviewing all things we present. Okay, so last time when I presented static root of trust for measurement, I showed exactly the same slide. The only difference is that now we're talking about dynamic root of trust for measurement. So this is this blue rectangle. It's placed in whole family of root of trust. It's dynamic because it does not require platform reset. So it can be done runtime, but there are two use cases of it that I will present. It's early launch and late launch. There are in general two most well-known implementation of that, which are made by CPU instructions. This is Intel senter and AMD SK init instructions. And just to not confuse things, despite this D-RTM and SRTM are on the same slide, those are very different things. SRTM is related to establishing some trust during on-platform reset, and the D-RTM can even extend. So both SRTM and D-RTM can exist in the lifetime of given platform, and it can add value to the platform security. This slide came from Trusted Computing Group Specification version 1 of Dynamic Root of Trust for Measurement. What is important on this slide is some general flow that all the RTM implementation use. So first of all, we have platform reset or platform power on. Then we may have in some implementation, this is in Intel implementation, this is present, some pre-gap configuration, so some preparation of the platform. So all the data required to perform further dynamic launch event will be configured. And then we proceed with some execution. It may be a static root of trust for measurement, firmware, and operating system that operates. And this is the gap. This is the area that the RTM wants to mitigate, and we just want to say that we don't care what happened at that time. DCE means D-RTM configuration environment, and this is because some execution of the RTM may require additional preparation before we can launch this special skinit or senter instruction. Then if DCE preamble succeed, that means we can proceed with dynamic launch event, which cause execution of dynamic DCE, DCE, which is the RTM configuration environment. And if the dynamic configuration environment succeed, we can run full dynamically launch measured environment, what means that we have some operating system or some application that was fully measured and securely executed thanks to the trust that we have in those special instruction senter or skinit. So DL event, thanks to those instructions and how those are implemented, extends the PCR 70 to 22 in TPM. Those PCRs are initialized with -1 right before DL event places the measurement in the PCRs. It resets that PCRs to 0, and then immediately extend with the hash of dynamically of the D-RTM configuration environment. And then, of course, if there will be any try to reset TPM, then the value of PCR will get back to -1. So then we are sure that the extension that we have in PCR 17 is always starting with 0, and then we add the hash of DCE. So this is like a whole spec, which you can read to dive deeper to understand how this really works. But let's see how the boot process of typical machine look like. For example, we have typically we have some boot firmware. This can be UEFI or coreboot. Then we have some bootloader. This probably is grub if we're using our Qubes OS. Then we have hypervisor, and then we have VMs. First VM is DOM0, and then DOM0 creates another VMs depending on our configuration. Of course, definitely this could be explained in more sophisticated way, but I just want to build the ground for further slides. Yeah. So okay, so there are two types of launches which use the RTM technology. First is early launch. Second is late launch. So how early launch works? So in case of our boot flow that I presented, if we use early launch, we will have something like on this slide. So from the left, we have UEFI or coreboot firmware. If this is Intel, we need special proprietary component, which is called BIOS ICM. It is distributed by Intel only to partners that have NDA signed. It has very questionable license and redistribution rights and all that stuff. We don't know what's inside, but it is necessary if we want to use Intel platform. For AMD platform, this component is not needed. Then firmware proceeds to start bootloader, for example, grab, and then grab, which already has some sample implementation of calling dynamic launch event, or in terminology of Trench boot, we will call that secure launch, just to unify the terminology. Grab can call this event, of course, doing some previously mentioned DCE preamble, preparing that environment so we can really do secure launch. And then we have this green rectangle which saying landing zone or sinit ACM. So landing zone is an open source component which you can find on Trenchboot repository. It's only for AMD, and sinit ACM can be downloaded for given platform from Intel website, and it is way different than BIOS ACM mentioned previously. And those components are exactly the DCE mentioned on the previous TCG slides. And then those components can execute dynamically and then proceed the measured boot from that point and run, for example, Zen, and then Zen boots DOM0 and all the VMs. So what is the value here? First of all, if we have SMI transfer monitor, which is special Intel stuff for controlling the SMIs and like adding security in case of SMIs in memory. Of course, there is AMD alternative to that. I don't know the name, but definitely it is present in specs. So they definitely have something. Then if we have those components, we can assume that we don't care about what UEFI or coreboot or whatever was before the secure launch caused to the platform. Of course, this is not fully true. This is very questionable, but that was the idea, just to remove that from trusted computing base and do not care about firmware and early bootloader phase. Of course, the other problems that we can avoid thanks to that is all this SRTM complexity. So we have all this technology like BootGuard, Intel Secure Boot. We have high Azure boot, hardware validated boot, first from NXP, then other from AMD. All those require NDAs. All those require special tools to be provisioned, and sometimes have convoluted specs. Very hard manufacturing process. We face that many times as 3M Dev, trying to enable our customers with massive SRTM deployments, and it's not easy. It's really complex, and it requires a lot of resources to make it work. So we can with D-RTM we can mitigate need for that and mitigate those problems. And of course, we can leverage values that are populated in PCR 17 to 22 because dynamic launch event just helps us populate those values, like do that for us in a secure way. And we are sure that we can use securely and in trusted manner those values to, for example, unseal some secrets or use those values for attestation. Then we have late launch scenario, which is way more complex than the previous one. Early launch is, to be honest, just the extension of SRTM, and it's hard to say what's the if we have open SRTM implementation, then it's hard to argue what's the additional value of early launch. But if we consider late launch as a use case for D-RTM usage in Qubes OS, for example, it may happen multiple times during the runtime of the platform. So on this diagram, what we have is, first of all, we have something that happened before running Zen. It can be some bootloader plus firmware. And then we have operating system with DOM0 and various VMs, like sysUSB, sysnet, sysfirewall, and all those VMs. And we can allow to almost any component use a secure launch or the dynamic launch event, and then execute our D-RTM configuration environment payload. This payload can be different for different cases, and I will explain that. This is like Flickr paper did that. They used various DCE payloads. What also can mean that further we can continue path in different ways, and this can build base for different scenarios. So one way is to have running virtual dynamically launched measured environment, and then get back to VM. What can cause for us is that we simply pause the VM and make some secure analysis, inspection of the system, and we get back to it, unpause it. But of course, this is like very complicated case. I believe like during discussion we can reveal more about that, especially that we have like great experts on the call. And other part is to relaunch whole platform. What means that we running the LME in hardware context, and in some way we communicate with Zen to coordinate the re-establishing trust into hypervisor, and then hypervisor of course continues execution, and I will have slide for that just to explain that deeper. This is way more complex but gives a lot of flexibility, and we can use various payloads, as I said, and we can call, to be honest, in this situation, we can call it as a secure execution environment. So without SGX or any of this enclave technology, we kind of getting special secure execution environment which has certain properties. Okay, so maybe let's get back to 2008 and paper presented and code also presented by McCune, Parno, and Peric. They created something called Flickr, which they explain as a technique for executing application calls as those DCE payloads. They call this DCA payloads piece of application logic. There is also SLB, which in their case is kind of library that provides some basic function to piece of application logic. If we look at this diagram, we see that there is need for some additional module. So they did that in Linux. They had Flickr module that they loaded. They have to accept some SLB, accept some inputs. These are like details described in the paper. But then they call the skinit instruction, which is kind of which is D-RTM instruction for AMD. And they, of course, everything's kind of paused at this point. All the processors are in skinit state, and there is execution of this Flickr session, which we want to implement or propose during this discussion for Qubes OS. We will not call it Flickr. This is like definitely something different, but the theory of operation is the same. So this some small application logic executes, then we clean up. There is extension of PCRs, and we resume OS execution. And what they did with that flow, what this gives. So they provide a couple interesting use cases. One use case was remote rootkit detector. So they just had system to which they established like a VPN channel and demanded to execute skinit instruction. And in skinit instruction, there was small code with checked kernel text segment, syscall table, loaded modules. It can check way more things. And then they measured that into the PCRs, into the TPM. Then they can use remote attestation to prove that those measurements were really made by this exactly rootkit detector, and that those measurements are true, because a system could not fake it because it's hardware protected secure execution environment. So then they created something like attested results for distributed application. So let's imagine SETI at home, where we had distributed computing environment, and we want to make sure that results provided by various computing units are not faked. So what we do, we just provide those execution paths, a piece of application logic, to all those computers, and we ask them to execute that code, and those results have to be attested and proven that this was really run by SKInit, and we are then sure that those results cannot be faked because hashes are hardware proved, if we can say. Or there were also other use cases like SSH password protection against malicious server, which is kind of more complicated case described in the paper, as well as private key secure storage. Since if you run D-RTM, you can seal secret based on the PCR values, and if PCR value 17, if you seal to PCR 17, then the value of that register can be reproduced only if the same code will be executed. So you are sure that always the same code touch the secret which you unseal using those values. Okay, so this was Flickr, and based on Flickr, we're trying to propose some scenarios that D-RTM may be used. So one of the scenarios is platform relaunch. It simply extends the case that I explained at the beginning. So first thing is that one of the components in the system, either VM, either the Zen, DOM0, runs secure launch. There is specially crafted DCE payload which runs our dynamically launched measured environment, which is kind of probably some small kernel plus initRD or maybe some program, which then pause all VMs and then checks the integrity of hypervisor. So why we check integrity of hypervisor? Since Zen controls the execution of secure launch, since this is hardware instruction, and if called in VM, it will cause VM exit, and then hypervisor have to handle that. Zen can also fake that, or either abort execution of SKInit or just try to fake the results of it. So because of that, we have to check if Zen integrity is intact, and then from that point we can start to we can, if it's okay, then we can pass control to it and can say, okay, let's continue execution and do whatever is needed, either recreate VM or create special VMs like measured and attest VM, which kind of can be used for attestation of other VMs. Yeah, so that's this case. There is also in Zen there is something called virtual machine inspection, or maybe this is general term, but Zen has this implemented. This is technique of checking the runtime state of the virtual machine. This can help in debugging or forensics analysis, but of course it can also help in checking the integrity and measuring whatever is running inside. So how we can use VMI? So for example, we can look at process table of running VM, and for example, check if critical system components are intact, have the hashes that we expect. So for example, we can check if the Vault, GPG, or sysvtpm VMs just have correct software running correct processes and there is nothing malicious there. We can have rootkit and malware detection, so we can look for some anomaly in VM. And we can also do some, for example, let's say we have admin VM. We want to change something in our Qubes OS infrastructure, like add VM, create some VM, or destroy some VM, or change something in configuration. Then we can say that we're checking administrative VM if all the processes that running on this VM are according to our expectation. Yeah, so when we connect VMI with our D-RTM, secure execution environment, this can bring additional use cases. So this is probably very small, but you can like enlarge your screen on YouTube. But this is try of explaining how this plays with VTPM. So in general, VTPM is not exactly needed if we're using dynamic large event instruction like skinit or senter, but it may be very useful in situation where we're trying to use virtual dynamic launch event or virtual secure launch instructions. So let's say our QEMU emulates skinit instruction or senter instruction. In that way, hypervisor can speed up the same process of late launch for only one given VM and re-establish trust in that VM or in the set of processes that running inside this VM. Yeah, and also, of course, if we want to perform any attestation or select secret or use select secrets, VTPM have to be present and available for application VM. So this slides explains some kind of maybe little bit complicated flow. So what it shows is like, let's say we're trying to start VM from some network location, from some HTTPS server. So of course we starting VM, we're sending the HTTP request, we're getting offer with the details about the server, about what we want to run. Then we're getting that stuff from HTTPS server. Meanwhile, of course, during the request there is certificate validation for the server. Then we load and then we can load and execute these components. But if we do this in a dynamic way, we can create virtual dynamic launch measured environment and kind of use whole profits that I explained before. So for example, so we're executing this skinit. If this instruction will be emulated by hypervisor, then we can extend our virtual PTPM PCRs. And then when continuing this boot flow, we may end up attesting the measurements of the environment that we created by simply using some attestation server, either local, either remote, which kind of should create a dynamically launch measured environment VM, which would be quite secure VM running and attested. Yeah, so maybe we can get back to that and try to discuss that slide further during the call. Other things that may happen, like if we have this ability of checking and inspecting those VMs, definitely there may be some indication, some runtime indication to user. So for example, right now Qubes OS use some colors like red, black, blue to indicate this is just arbitrarily selected colors. They don't mean anything at this point, but in future changing those color may have some meaning, and it could be connected to this runtime attestation on runtime inspection of the VMs that we have. So for example, we may have some policies that say, okay, we can run the given action only if given VM is not red, for example, or only if it is black, and so on and so on. how we change those colors? Of course, we change those colors by running D-RTM and inspecting the VM process table and on all other needed components to make sure that we trust this VM at this level. Yeah, so first of all, early launch can be used to assign those colors at boot time. This also can be also SRTM, I believe, can be used to some extent for that. And then late launch may change those colors, so we can see that. For example, we use Qubes OS laptop. We use it for some time, but we left the laptop for whatever reason, or we just did S3 sleep, but we get back, and then there should be run of D-RTM across all VMs, and we should check if the integrity of those VMs didn't change, or at least it should be indicated to the user by correct color. So this is some idea. So what other ideas we can have here? So for example, we may use VDLME or DLME for backups or migration of the system. So let's say I have new laptop, I want to migrate my Qubes OS to new laptop, or I want to backup my my Qubes OS. Of course, I want to do that in very trusted and measured and attested way. Then we have a thing that we're doing right now for Qubes OS, which is fwupd implementation. But we can imagine that fwupd is run in D-RTM. Of course, the question is what's the access to hardware, but we can kind of extract the critical part of fwupd and put that in this trusted environment. Other thing is we could have dynamically changing RPC policy. So we may want to run some application on some VMs, but then policy can say like you cannot do that because the trust of this VM changed, and according to policy it should not happen. Then we may have, for example, some pools of VMs, like we have like this pool have like very good trust because we know all the components that are running there. This has less trust because there is some small misconfiguration, and this has no trust because there are some weird processes running inside. But that's I believe that's a good question for Marek, and like this definitely would require some extension to Qubes RPC implementation. Secure storage, so we can of course use that for sealing secrets, as I mentioned before, and say that some secrets are only available to some DCE payloads. So for example, we may have some DCE payloads related to payment, related to VPN, related to some SSH. The question is what would be the performance of that? This could be questionable at some point. So maybe VTPM implementation could help with the performance of that. And of course, we can, in that way, we can also try to implement per VPN password managers. Yeah, but maybe there will be like other ways for that. So yeah, so to finish my presentation, I would like to discuss what you think about that, especially late launch. Like I spent not enough time reading the research papers, and this is quite complex to grasp all the components of late launch. Question is how far we are from that. It seems to be quite a lot of work. Also, how we can do the attestation in Qubes OS. Of course, we don't want to rely on network connectivity, so maybe we should have like local measured and attestation domain, as Daniel at some point suggested, or maybe we should have some additional hardware components that help us with that. That will also be interesting. Or what kind of other ideas for late launch and early launch in systems like Qubes OS you see? Okay, that would be it.
Okay. Thank you for the
So
presentation.
Yeah.
Yeah. Okay, so maybe I will start with some questions.
Sure.
How in case of late launch, how devices and especially DMA capable devices are handled in this case?
It's complicated.
When you do late launch,
so
when you do late launch,
in both cases with SEnter and with SKinit, both of these technologies predate IOMMUs in the CPUs. So both of them have mechanisms for DMA protection of the measured region. It's expected that one of the early things you do during setting up the measurement environment is to use the IOMMU to provide DMA protection for other areas you wish to measure and use.
Yeah, I believe it may happen that we need more flexible IOMMU, and I don't know if all IOMMUs will provide enough flexibility to handle late launch correctly. I don't know, Daniel?
Yeah, so it actually varies between the two architectures. So on Intel, they use the PMRs within the VTD to protect just a block of memory for the duration of the launch until the IOMMU could be more initialized with a full page table and everything. Whereas on AMD, they use a different mechanism to protect that. So
there's also the DPR for older Intel hardware.
I'm sorry, which one?
DPR, DMA protected region, which is initialized by BIOS, and I think it protects the SINIT memory and TXT heap memory.
Yes. So those are set up by the BIOS ACM on when you have a TXT enabled platform. So those regions are protected, so they can't, during their life cycle, they can't really be tampered with. And then when the ACM itself executes, as was in the discussion on the LKML, the ACM actually executes inside of ACRAM as opposed to general memory, whereas on AMD, the secure loader executes in general memory protected by the DEV, the device exclusion vector. So yeah, that's, and then on top of it, when the instruction is called, all interrupts have been paused for at least a portion of the launch, and then you're kind of in control when those get re-enabled. And I think that covers most of the protections.
Okay, that sounds reasonable, I think. Okay, so when we are doing late launch, what would be the best way to reestablish trust in the platform? Because I see basically two approaches. One is measure the existing system software running and return the measurements if everything is okay, and the other one is performing I would call live update, like a restart, like bootstrap the hypervisor again and simply migrate the parts we care about from the old system. So do you have any thoughts about that? Which is better, which is easier to implement, and also which one is more reliable.
Andrew, Daniel?
So each one has its complication, right? So, and what Piotr presented here, he basically was discussing leaving Zen in memory and doing a measurement of the in-memory code of the Zen hypervisor. Obviously, that means you need to be able to have the capability to do runtime inspection of Zen. And then with the other approach that you kind of just suggested, which would be the devil's in the details, so I don't know which one would be more complex, but it would be interesting to see of reloading a new instance of Zen and then making it aware of, hold on.
Technical details. Yeah. Daniel, are you back with us?
Okay, technical break.
Well, okay, so I can continue this a little bit. We are certainly finding at the moment that
I would leave
the ability to maintain the system as a whole is quite difficult, which is why at the moment we're focusing on the early, on getting the early D-RTM into a working state. So that involves taking the IOMMU from whatever state it's in and programming it sensibly, so you can measure the Zen binary in memory, you can measure the DOM0 binary and the init.rd and whatever else you've got launched at that time. That is definitely going to have to be separate to what a runtime, what a late DLME would look like. And there are some details that are open questions with the vendors at the moment. We suspect to make this sensibly usable, we probably are going to have to request some changes. It's certainly possible that we could rerun it late at the time, but we'd have to stop the system, tear the IOMMU down, reprogram it safely, do the measurements, put it back to how it was. And that you cannot do that without making a meaningful interruption to the system.
Yeah. So, yeah, either way, it's going to be very complicated. You know, and as Andrew was saying, is that, you know, the first steps is once we start to be able to directly late launch Zen, so we can at least do that. It will be the first step, and then later steps here that Piotr's laying out would be things that we could build upon, and it would give us time to get requirements fed into the manufacturers to see if we can influence them to help enable some of this.
Yeah. So from my point of view, it doesn't look like those D-RTM features going anywhere. But you know, if we will. So definitely this is complex. I understand how complex it is. Like maybe I don't understand all the details, but I see that it's very hard to grasp all the picture. But if we will start slowly push something and try something, experiment, see what's wrong, what paths to choose, and discuss and communicate with the community that some experiments happen, then it would be definitely easier to construct something working example, and maybe even, you know, some simple cases will work. Not you know, I definitely do not see that this is like Qubes OS feature for next release or even 4.2. It's rather way longer approach. But if we're discussing about that, it's already first step.
Yes, I wholly agree. You know, they're definitely, this is the idea, and then we just need to start trying things and seeing how well it'll work, what will fail, and start laying roadmaps for being able to get to something like what you've laid out here today.
Yeah.
Yep. Okay. I have also a question about this local attestation, because with purely local attestation, I think it's impossible to present some meaningful result, because whatever you are attesting to could be emulated if you don't have some previously established root of trust. Am I missing something, or how that would work?
So a local attestation usually boils down to doing some kind of an unseal operation with the TPM. So in that case, yes, if you have not completely provisioned your TPM, you could, in theory, emulate it. There was a paper done several years ago by Siege Technologies in which they demonstrated that. If you have a provisioned TPM, then a properly provisioned TPM, it would not be capable of being emulated.
Mm-hmm.
Ultimately,
Okay,
you can
so
take ultimately you can take a piece of hardware, stick a secret in the TPM, and work with it in a secure way. But you have no way of knowing whether that's a real piece of hardware or a sufficiently good hypervisor that's emulating the entire system. The only way to establish trust is to be able to provision a known good secret into what you believe is the hardware TPM. And no amount of technology at this stage can cope with that not having been done correctly to begin with.
Right. So that's the properly provisioning of the TPM, right? You've derived, so every TPM has a secret that was put into it by the manufacturer, and you can use that to derive a certificate that's signed by the enterprise, and then you can use that public key to know whether or not you're actually communicating with the provisioned TPM or an emulated one.
Yeah, so the other way is definitely like combine that with SRTM, but this can defeat the purpose, because of course, like if machine is running very long, we may like kind of lost the trust in, like, decide that it's like everything could happen in memory. But if we decide that like, you know, SRTM is good enough for hypervisor at least, then maybe maybe this combination of SRTM plus D-RTM also can give some benefits. Like, definitely this is not ultimate solution, but maybe some middle ground, or some, you know, not all threat models are the same. Yeah.
So one thing that,
okay, so
even if it's only with the early launch, so the one straight out of boot, what you get from that is a measurement and integrity of the system that does not include any of the EFI boot time services. It doesn't include anything Grub did. The only thing it includes is the measurement environment itself, so the bit of code that's currently running and on the system, and the SMM handler, which was previously established.
Mm-hmm. So it's not enough.
It's not enough. So this is where the STM technology comes in that Intel did, the secure transfer mode, which basically lets you put in a bit of auditing to check that the SMM handler keeps itself to itself in a predefined way. So it allows you to protect. It allows you to prevent the SMM handler running out of the area it shouldn't be running in, but it doesn't allow you to actually take control of the SMM handler itself. AMD do have a way of doing that, but I've forgotten the details of it right now.
Yeah.
So that there are definitely mechanisms whereby using late launch can allow you to get integrity, or at least a vague idea of integrity of everything running on the system, even if you are not necessarily in a position to change the SMM handler directly.
Okay.
And even that gives you a better default
so
starting position than just static root of trust.
Okay. Got it.
Yes, yes. Okay, so this is basically kind of trust on first use. Like if you have some, if you do your provisioning on something you believe is the real hardware in a state you like it to be, then later you can attest if it's still in the same state. Is that correct summary?
So not necessarily. So when you use the SRTM, there's so many things that go into the SRTM measurements that the only thing you can do today is a trust on first use when you use SRTM. D-RTM, all the components that are involved in the D-RTM when you have an STM in place is everything that you can know the measurements beforehand. So that way it's not necessarily a trust on first use. You could actually verify everything before you ever load the platform. Because there is not the amount of dynamic things measured into the SRTM and the fact that there's an inconsistency in UEFI manufacturers and how they're generating those measurements makes it very hard to do anything other than trust on first use with SRTM. Whereas in the D-RTM, the individual user can have a lot more control over it, and in the Intel case, the handful of components that you can't have that Intel has control over, Intel could publish exactly what it is because it's not a lot that is in Intel's control.
Okay, so what exactly in the current state are the components that are included in the measurements that are specific to some specific piece of hardware? Is it SMM handler, right? Anything else?
So on an Intel platform, it would be the STM. Along with the SMI handler, the virtual SMI handlers that are implemented inside of it. And then it would be the ACM as well. And those are the only components that would be produced by Intel or the manufacturer that would not be under your control. Everything else outside of that on an Intel platform, it would be under the owner's control. On AMD, like as everybody pointed out, there is an equivalent to the STM, but nobody recalls exactly the details of it. So I don't know how much of that how much is involved in that, but those components would be under the control of the OEM and AMD. Now, the equivalent to the ACM on AMD is actually user provided. That's the landing zone, if you saw that in some of Piotr's slides. So the landing zone is something we would get to, right there, the little green blob between there. So that is right now being written by the Trench Boot project, thanks to Piotr and Andrew. So those are under the user's control, and the user can can take the reference implementation that we're working on inside of Trench Boot and build their own from that.
So Marek, like the Intel part is not so, I would say, cool for open source people. Definitely so first of all, BIOS ACM is a huge problem, but probably most of the people watching that, most of the Qubes OS user just assume that UEFI is there. Okay, my laptop has UEFI, and okay, it's vPro laptop. It got BIOS ACM, so it's together. All that is provided. Key point probably would be, okay, measurement of BIOS ACM. Where I will get that? Who will provide that? Is whatever ACM I have is trusted? Yeah. So this is a problem. On AMD, this is not a problem. So for example, for KGP D16, we can have fully, completely open source implementation. Yeah. So landing zone is AMD stuff. Open source implementation on Trendwood GitHub. So that's good one. There is no blobs. There are no blobs. You can run without microcode even. There is no PSP. So there is, but of course, platform is quite old. Yeah. I believe the laptops X230. So this is Sandy Bridge. So it requires ACM, and I already talked with Thierry about this part, and this is a huge problem. I also talked with Brian Richardson about that. 3MDEP got access to BIOS ACM, and we can construct that for as a service for our, if we provide BIOS for someone. But still, this is some binary. Someone have to trust 3MDEP, for example, and we have to trust Intel that provided that binary. So Intel is problematic. The STM part is also problematic, but then the problem is for AMD side, because AMD kind of there is no known implementation for that, and we don't know the SMI transfer monitor STM for Intel is more well known, despite not so massively used, because I never saw that in the open use it massively. It's just I know it's in coreboot, but we never faced anyone requesting that or anyone wanting that. Definitely, maybe there are people that using coreboot with STM, but yeah, still STM, using STM or AMD equivalent would be needed. Yeah, so the problems, and of course SINT ACM, which is loaded by Grab, is also closed source binary. Yeah, so that's kind of Intel part, and maybe this will change in future.
On a pragmatic point of view, yes, there are closed parts here, but ultimately you're trusting Intel anyway for your CPU. You might as well trust them on some of the binary blobs they're providing. A number of them can at least be inspected, so you can see what they're doing, even if you are not at liberty to change them. And arguably, that's better than nothing at all.
So Andrew, I'm just maybe looking more from with open source firmware consulting company.
I completely agree that where relevant, it would be better to have everything open. On your point about being able to run an x86 CPU without microcode, I'm afraid that doesn't exist. There is the majority of the microcode is already burnt in at manufacture time.
Okay.
In some cases, the microcode you change via a microcode load is only a tiny fraction of the microcode in the processor.
Okay, yeah, I'm just saying, like, there is no so the processor you're getting, it was whatever you get, you have to trust, because otherwise, if you don't trust that, then your threat model is kind of weird or are like extremely paranoid. But if you also, like, I believe it is a problem that you're getting binary components, and to be honest, the people that provide you this binary components does not give you ability to correctly verify that binary components. If it's like, I know that BIOS ACM is signed, but from perspective of firmware developers that want to provide good hardware with good firmware for open source community, it's huge problem. It's like with SRTM, all these pieces are very problematic. It's hard to discuss with those vendors, and it doesn't seem that they will change the behavior in future. So I would be even fine with binary components if they will kind of in good manner and with goodwill help in trusting those components and making sure that those were not changed at any point. And we at least, if they change, they at least publish what they changed, why they changed. This is like huge problem. They like don't care about informing whatever happens inside firmware components and closed source binary. You're just taking that and have to believe in that. So yeah, that's kind of my.
I will completely agree with that as a problem.
Yeah.
I'm probably not say much more than that.
Yeah, Marek, give us more Qubes OS because we kind of dominating that in driving that in not correct. Let's take 10 minutes more from this part.
Actually, I'm almost run out of my questions for this presentation. I have one more, which is, I think, also mentioned last week regarding measurements of the system. Like, what would be a reasonably part of the system you need to measure to give some assertions like this VM is really isolated from, I don't know, network or other VMs and stuff like that. So that definitely would need to include hypervisor. But I wonder how we can make this measured software, this trusted code base, basically as small as possible here. Is this,
I don't know, Christian, can you, Daniel is still here. Maybe Daniel will help me with that because it's tricky.
So the answer to that would be the HAT architecture I presented at PSEC, right? Break the system down into to minimize privilege of how much privilege each component can have, and restrict the responsibilities to the roles that they're providing, and ensure that the implementation only has enough code to do those functions, and then you can sit there and measure each component and build up the integrity of the entire platform from there.
Yeah, so for example, like Marek, my kind of, I imagine something like that. Like I have this sysvtpm, yeah, and I know what kind of process with what kind of memory layout and what kernel should be run there. It should be very small. I should have full knowledge about runtime capabilities and parameters of that VM, yeah. And to be honest, like we discussed that that there probably will be many of those VMs. So if I do this measurement and like check runtime check if everything is fine, I should be able to pretty well define what I want to check, what kind of parameters, what kind of processes running there, and what I expect is trusted and what I expect is misbehavior.
So, and actually to add on to it, to bring it to a little more practical approach, I'm assisting with delivering the boot domain capability to Zen. So we actually have a proof of concept working now where we can boot Zen on x86 without a DOM0 ever existing. We actually can spawn a hardware domain and then spawn, which along with some guest domains, some DOM-Us, and unpause it all and have it all take control without ever having gone through a DOM0 to get to that system.
Yeah, so you mean, Daniel, that just measuring this DOM-B, or like what does it mean? Like what does it mean in context of measuring components and which components we trust?
Right. So if you look using the slide you have up on the screen right now, when you launch Zen, you would actually, instead of having just a DOM0 right there, you would have a small boot domain along with all of your DOM-Us over here and all your other domains off into the blue set there paused. The boot domain can be a small ideally it could be a small real-time or unikernel kind of system, which is that can be quickly measured, and in itself can work with Zen to measure all of the domains that it's going to start without having to unpause them, and record those measurements before you turn control over to your actual target system. So,
Okay,
so what does it mean? What does it mean?
We can do similar thing in late launch, right? Pause everything, do measurements of those VMs, use some small, maybe unikernel or something like that, and then resume, right?
yes. That's exactly where it's going. So,
and also make sure that
yeah.
I think we also need to measure XSM policy or some equivalent to make sure that all the domains have only privileges they really need.
Yes.
I'm terribly sorry. I'm going to have to drop and go on to a different Zen call at the moment. So
thank you, Andrew.
Thank you very much.
Bye-bye.
Thank you.
Yeah. So yes, that is exactly where we're going with this, is that you can now, everything can, we're laying the foundation, that breaking us all up for a standard Zen boot, and then you can layer on the D-RTM on top of it that can work in conjunction with all of this to make sure everything is measured and controlled before anything is allowed to take control of the system. Any of your target stuff. So any of your hardware domain, before your hardware domain can have control, before all of your DOM-Us can start running, your sys firewall, all that stuff, you can make sure everything is in a good state and attested to before you unpause the system. And it's done such that the boot domain does not have any privileges outside of what it needs to unpause the domains. And so you have this very controlled environment where you can do the attestations and before you allow the platform to move on.
So Daniel, do you mean like this is this pausing and inspection use VMI, or this is like something different?
This is if you wanted to run a VM, so you wouldn't necessarily need to do a VMI, because at this point we're talking about the early launch scenario, whereby the Zen has been brought in, all the DOM-Us have been brought in, everything got measured as part of the D-RTM, and now you're inside of your boot domain, and your boot domain can do, look at certain things and be able to do, we can control what it needs to take care of to make sure that the platform is healthy before it allows it to continue to start within the context of the Zen environment.
Okay.
So you'd use the D-RTM to make sure that Zen is good and the boot domain is doing good, and you measure everything else, and then you go into your DOM, into your boot domain, and your boot domain can now do the next step of integrity checking and attestations that you might want to do before you allow the system to continue.
Okay, so that means that we really kind of trying to defeat the SRTM because like that sounds like if you're saying early launch, that this is the usage model, and that's the and probably early launch, the most biggest value is that we kind of forget about whatever was before, like firmware stuff. We don't care about that. But of course, we need this ACM stuff, hashes, and we need STM from firmware. And the question is if we can detect that, if we have that, and kind of make some action if we don't have that.
So the way to think of this is laying the groundwork, just like how we're doing early launch for Zen first, and then we work on late launch. The laying of the groundwork in the early launch is, being able to make Zen more flexible in how it's able to start a system. Okay. And so that way we come back around. So later, when we want to be able to start looking at how to make Zen do a late launch, we've already started to break the stuff up, and a lot of the codified assumptions of a classic start have now been broken, so that a way it makes it easier so that we can start looking at how to relaunch a Zen system.
Okay, yeah. So that means like probably some serious changes to Zen.
Yes, we are definitely changing the boot path of Zen with the boot domain logic.
I see that we have some question from YouTube, from Bobby. Hey Daniel, what was the company that published the paper on emulating the TPM unseal operation for a non-completely provisioned TPM? It sounds like Siege technology. Siege, I believe Siege. Yeah. Like, yeah. Daniel, is that correct? Siege technology? Like, I'm not sure if you see the questions in YouTube chat. Okay, got it. So that's great. That's great that Bobby listens us. So thank you for that. Okay, I believe like we should move on. Like that's very interesting discussion. I don't know, Daniel, if you can stay, but Michał will show some, I don't know, demo maybe even of.
Unfortunately, there will be no demo.
Okay, but you will describe what was the problem.
Yeah, demo. I will describe why demo is not working.
Okay, that's fine, but this would be way more practical than this theoretical discussion that we have here. But this is like early launch stuff, yeah.
Right.
Early launch on Intel with coreboot. Okay, so let's switch to Michał.